I saw him today.
Greetings and welcome, friends who are seen and unseen. Perhaps you're from some sort of ethereal realm where we can't quite see which dimensions you're operating in, but that's fine. Welcome. We're taking a look at modeling motion using parametric equations, two-dimensionally, of course. So those of you who live beyond those dimensions, this video might not make sense to you. And we're on page 531, and here's question 11. It says, find the initial and horizontal velocity, the initial horizontal velocity and vertical velocity for each situation. So a cannon shell fired 1,200 feet per second at an angle of 42 degrees. So here's my 42-degree angle. That's a little larger than 42 by the looks of it. And the initial velocity is at 1,200 feet per second, right? So I want to find the initial horizontal, and the initial vertical forces, which of course form some sort of 90-degree angle with one another. So we actually, I think, had some little formulas for this where x was equal to the cosine, or what was it? How did we label it? The magnitude of vector v multiplied by the cosine of theta. And y was equal to the magnitude of vector v multiplied by the sine of theta. Something to that effect. So in order to do this, I merely have to make those calculations. So x is equal to 1,200 times cosine of 42, which is going to be about 891.774 feet per second. All right, right. And y is going to equal 1,200 times the sine of 42, also not too difficult to determine. And you get, oh, that's 12, not 1,200. 802.957. And by the way, if this was launched at a 45-degree angle, both the horizontal and vertical forces would be the same, and that's actually how typically you could accomplish maximum distance for a projectile, is right shooting off at a 45-degree angle. That'll give you your maximum distance. So here's question 17, which I hear was a little bit tougher. So Alfredo and Kanicia are performing a physics experiment. Like I was excited about a performance here for a second there. In which they will launch a model rocket. The rocket is supposed to release a parachute 300 feet in the air. Oh man, guys, this is terrifying. 7 seconds after liftoff. Oh boy. They are firing the rocket at a 78-degree angle from the horizontal. What are you doing? Oh my goodness. Find the initial velocity of the rocket. Wait a minute. Oh, right. Okay. Well, so let's consider our two equations. So x is going to equal t times vector v's magnitude times the cosine of theta. Right, that's our starter, parametric. And y is equal to t times v times the sine of theta minus, what's it, 1/2 gt squared? Oh yeah, there it is. So there's our two equations. And notice the clues that they gave us. They told us that at y equals 300 feet, which time is equal to 7 seconds, all right, that something is supposed to happen. They also told us that theta is equal to 78 degrees. All right, so it's only going, once we throw this parachute out or whatever, or release it into the wild, it's going to no longer have a trajectory matching these formulas, right? It's going to be messed up by wind resistance more significantly. So this looks like information I could plug into an equation. It looks like I could plug in, I know t, I know y, I know theta, I know that t. Do I know g? Well, they're using feet, so I imagine that g should equal, yeah, the 32 feet per second squared. That is given information based on the fact that this problem comes from a math book on planet Earth.
It's the same as 9.8.
Yep, 9.8 meters per second squared or 32 feet per second squared. Those are typical planet Earth conditions for gravity's acceleration, although they can change varying on elevation. So, find the initial velocity of the rocket. So, for part A, let's just plug in what we know and solve for what we don't. So 300 is equal to 7 times, I'm just going to call it V, I think we're cool with that, times the sine of 32 degrees minus half of 32 is 16, wait, 78, sorry, it was a 78 degree angle, my bad. Minus half of 32 is 16, t squared, so that's 7 squared. Bam. So I'm just going to go through and solve this, my friends. So let's see. We'll do a little math first, I guess. 300 equals, let's see, what's 7 times the sine of 78? That's 6.847 times my velocity. Minus 16 times 49, or 7 squared, is 784. So plug in what you know and solve for what you don't. It's called algebra. So here we go. 1084 equals 6.847 times the velocity. And then divide both sides by that 6.847. And I should get an approximate initial velocity. Plus, let's see, 300 divided by 6.847. And I get 158.318 feet per second is my initial velocity. And I guess now that I'm labeling it, I can properly give it magnitude and vector status. So that's part A. That was plugging in what I know. So I just want to point out that calculating the initial velocity, right, for in the case of a rocket where maybe the initial velocity would be an unknown to you, right, might not necessarily say that on the box of the rocket you built, that we could calculate it based off of data that's gathered, all right? So, you know, if you gathered data using whatever means you had and angles and planet Earth, you could figure that out. Let's see, let's look at part B. It says to protect other students from falling rockets. Oh man. The teacher needs to place warning signs 50 yards from where the parachute is released. How far should the signs be from the point where the rockets are launched? Okay. First of all, the guy's a jerk because he just done and gone converted to yards. So 50 yards, what would I multiply by to convert to feet? 3 feet per 1 yard. Right. So that's 150 feet. Okay. And let's see, from where the parachute is released. So I think they're assuming like some sort of a roughly vertical fall after the parachute's out is going to occur. And I mean, it's falling with a parachute. I don't know how much danger there is. I have a friend who lives up on Hogback Mountain. From what I understand, he's been able to launch rockets and then catch them, which is amazing. But he doesn't launch it from Hogback. I think he launches it like out in big fields. But yeah, so like if it's coming down slow, right, is my point. Right? So how far should the signs be placed? So what I'm interested in is I want to figure out, I'm interested in what's going on horizontally speaking, right? Where's the location of the rocket at these given times? So I'm going to use this vector times the cosine of theta, right, formula. the initial velocity. So we'll get x is equal to, what was it, 158.318 multiplied by the cosine of 78 degrees. And I'll get x equals multiplied by cosine 78 degrees. And this is in feet. So this is horizontally how far over the rocket had traveled. Okay, so imagine we launched our rocket, right, and then right here it like releases the parachute, safety parachute, right, and there's like a little parachute, then the rocket comes down, right, there's my awesome rocket, bam, and it's gonna fall, right? So so it falls. What I'm claiming is that this horizontal distance is 32.916 feet. Now, wait a minute. They converted their answer back to yards. Wait a minute, what? Let's see, wait. We were working in feet earlier, right? Yeah. So all my other units were feet per second. Seconds, yeah, feet, seconds, we're good. So, yeah, so I should be able to add 150 to this, but I don't think that's going to be 127 yards. Oh, no, because it's asking how far the sign should be placed from where the rocket is launched. So that's x equals 0 speak. Maybe. Well, anyways, I'd want to add 150 to this, right? Feet. And that's a total of 182.916 feet. Or I technically also have to worry about what if it goes back this way. Yeah, did I make a mistake on this, guys? Uh-oh. I got that right. I'm in the right mode. Yeah, I'm in degrees. What was the answer to part A? Let's verify part A first. The answer to part A was right. So I've got some verification. 158 point, okay. Oh man, I'm sliding all over the place. Well, oh guys, you didn't save me here, guys.
Why? Do you want to do that other one?
We forgot about time. Time. And that was what, 7 seconds in there, right? So 7 times that number. That'll do it. So x equals 230.412 feet. There we go. There's your problem. So yeah, so this number is way different. But actually the scale of this is going to be a little bit varied now too. So think about this. So this is 230-ish. I not only have to worry about 150 feet this way, but also this way. Right? So I'd be interested in what is 230 plus or minus 150. Would give me those two kind of ranges there. Right? So 230 minus 150, I would say 80.412 feet. To 230 plus 250, which is 380.412 feet. Okay? Which, if we want that in yards, dividing by 3, now I get the 126.8. So I'd want to point out that he's marking danger signs on this side. What about over here? Right? Like, That's the one that's closer to the students that are firing it. At least I would think so. Yeah, but I guess maybe like if the school building's over here and like students are walking around this way, they're the ones you have to warn. These guys, they're all ready for it.
Why are you on 50 is 50 years?
I don't think it should be
Yeah.
80.4.
You don't think what?
I don't think it'd be 80.4. It should really be something else. The decimals, right?
Nope, no, it worked
Wow,
out.
you're right.
But anyways, so thanks for watching, friends. Sorry I've lost track of time.